Hello everyone. In this section of Electronics 1, we will discuss one diode application, rectifier circuits. Rectifier circuits are one stage inside a DC power supply. Since the voltage provided by power plants is an AC voltage, it usually has to pass through a transformer, a rectifier, a filter, and a voltage regulator before it becomes a DC supply. The role of the rectifier is to convert a bipolar voltage, which has both positive and negative polarity, into a voltage with only one polarity. First, we introduce the half-wave rectifier. As shown on the right, it consists of a diode D in series with a resistor R, and the voltage across R is taken as the output voltage. For the diode, we can use the constant voltage drop model to perform an approximate analysis. In this model, if the diode is reverse biased, or even if it is forward biased but the applied voltage is still below about 0.7 volts, called VD, there is no conduction current. Therefore, the diode is modeled as an open circuit, as shown on the right. The output voltage VO is 0. When the diode is forward biased and the applied voltage is greater than 0.7 volts, or VD, the diode turns on. Its resistance is approximated as 0, so the equivalent circuit is a short circuit with a fixed voltage drop of VD, about 0.7 volts across it. From this model, we can obtain the relationship between the input signal Vs and the output voltage VO. When Vs is smaller than Vd, the diode is open, so no current flows through R and the voltage across the resistor is 0. When Vs is larger than Vd, the diode drops only Vd and otherwise behaves like a short circuit. Therefore, the extra voltage beyond Vd appears across R, so VO equals Vs minus Vd. Now suppose the input voltage Vs is an AC sine wave, as shown by the red curve. After passing through this circuit, whenever Vs is smaller than Vd, the diode remains open, no current flows through R, and the output voltage is 0. When Vs is greater than Vd, VO equals Vs minus Vd, so the output waveform looks like the input waveform shifted downward by Vd, as shown by the blue curve. Because the diode conducts only during the positive part of the input cycle, where Vs exceeds Vd, the output appears for only about half of the signal period. That is why this circuit is called a half-wave rectifier. Also, because the diode needs about 0.7 volts to turn on, this rectifier cannot rectify very small AC amplitudes. For example, a 0.1 volt AC signal cannot turn on the diode at all. Another important point in rectifier design is the maximum reverse voltage that the diode must withstand when it is off. This is called the peak inverse voltage, or PIV. If the reverse voltage exceeds the diode limit, reverse breakdown can occur, producing a large current, and the circuit will no longer behave as a rectifier. In this half-wave rectifier, during the negative half cycle of Vs, the diode is reverse biased. The cathode is at 0 volts and the anode is at Vs. When Vs reaches negative Vp, the magnitude of the reverse voltage across the diode is Vp. Therefore, the PIV equals Vp. In rectifier design, the diode breakdown voltage VBD is preferably at least 50% higher than the required PIV. After introducing the half-wave rectifier, we now move on to the full-wave rectifier. As the name suggests, a full-wave rectifier can rectify almost the entire cycle of the input signal. The circuit shown here is called a center-tapped rectifier. It is a simple full-wave rectifier. The original AC voltage first passes through a transformer, which adjusts the AC amplitude to Vs, and then the rectifier converts it into a single polarity output voltage. A center-tapped rectifier essentially sends the transformed Vs into two half-wave rectifier paths. Clearly, the upper part of the circuit is the half-wave rectifier we just discussed. The waveforms of VO and Vs are shown on the right. When Vs is in the positive half cycle, diode D1 conducts and transfers the input signal to the output node. Let us use an extreme case to explain the operation. When Vs reaches the positive peak, Vp, we first check the ground reference. The anode of D1 is at positive Vp, while the anode of D2 is at negative Vp. Therefore, D1 has a higher anode voltage and is forward biased, so it turns on. D2 has a lower anode voltage and is reverse biased, so it remains off. After D1 turns on, the cathode voltage of D1 becomes positive Vp minus Vd because a conducting diode drops Vd according to the constant voltage drop model. The cathode of D2 is connected to the same node, so the voltage across D2 becomes negative, with a magnitude equal to the quantity 2 Vp minus Vd. This reverse voltage is the PIV of D2. Therefore, when Vs is in the positive half cycle and its amplitude is larger than Vd, the output voltage Vo equals Vs minus Vd, giving a positive output voltage. Next, when Vs enters the negative half cycle, take the peak value negative Vp as an example. The anode of D1 is now at negative Vp, so D1 is reverse biased and remains off. The anode of D2 is at positive Vp, so D2 is forward biased and turns on. Therefore, the cathode of D2 is at positive Vp minus Vd, and Vo also equals positive Vp minus Vd. The output is still a positive voltage, and the PIV of D1 is 2 Vp minus Vd. We can summarize the center-tapped rectifier as follows. When Vs is positive and greater than Vd, D1 turns on and D2 turns off, so Vo equals Vs minus Vd. When Vs is negative and the absolute value of Vs is greater than Vd, D2 turns on and D1 turns off, so Vo equals the absolute value of Vs minus Vd. This gives the transfer characteristic between Vs and Vo shown on the right. If the input Vs is a sine wave, then regardless of whether Vs is in the positive half cycle or the negative half cycle, the output Vo always has a single positive polarity. This is the function of a full-wave rectifier. However, one drawback of the center-tapped rectifier is that the required PIV of each diode is high. It is 2 Vp minus Vd, which is almost twice the PIV of the half-wave rectifier. To improve this drawback, we introduce another full-wave rectifier circuit, the bridge rectifier. The circuit shown here is a bridge rectifier. It consists of 4 diodes and 1 resistor, and the output voltage Vo is the voltage across the resistor. Notice that the anode of D1 is shorted to the cathode of D4, so D1 and D4 cannot be forward biased at the same time. Similarly, D2 and D3 also cannot conduct at the same time. When the AC input Vs is in the positive half cycle, take Vs equal to Vp as an example. The anode of D1 and the cathode of D4 are at a high potential. Therefore, D1 turns on and D4 turns off. After the current passes through D1, it reaches the cathode of D3, so D3 is reverse biased and remains off. The current then flows through the resistor, reaches the anode of D2, and turns on D2 before returning to the low potential side of Vs. Therefore, during the positive half cycle, the conducting path is D1, the resistor, and D2. D3 and D4 are off. During the positive peak, Vp is the total voltage across the conducting loop. It equals the voltage drop across D1 plus the output voltage Vo across the resistor plus the voltage drop across D2. Since both D1 and D2 are conducting, each diode drops Vd. Therefore, Vp equals Vo plus 2 Vd, and Vo equals Vp minus 2 Vd. This also means that D1 and D2 can both conduct only when the positive input voltage is greater than 2 Vd. At the same time, we also check the PIV of D3 and D4 during the positive peak. Since Vs equals Vp, the potential difference between the cathode of D4 and the anode of D3 is Vp. Because D2 is conducting, one diode drop Vd is already taken away from the peak voltage. Therefore, the reverse voltage across D4 is Vp minus Vd. By the same reasoning, the reverse voltage across D3 is also Vp minus Vd. So the PIV of D3 and D4 is Vp minus Vd, which is almost half of the center-tapped rectifier value, 2 Vp minus Vd. Now consider the negative half cycle, using Vs equal to negative Vp as the example. The high potential side is now at the anode of D3 and the cathode of D2. Therefore, D2 is reverse biased and remains off, while D3 turns on. After the signal passes through D3, it reaches the cathode of D1, so D1 is also reverse biased and remains off. The current then flows through the resistor, reaches the anode of D4, turns on D4, and returns to Vs to complete the loop. The total loop voltage is negative Vp, which equals the negative of the quantity Vo plus 2 Vd. Therefore, Vo equals Vp minus 2 Vd, giving a positive output voltage again. The PIV of the off diodes, D1 and D2, is also Vp minus Vd, which is almost half of the center-tapped rectifier PIV. Therefore, the final output waveform is a full-wave rectified waveform, as shown in the diagram. Compared with the center-tapped full-wave rectifier, the bridge rectifier has a slightly smaller output peak because 2 conducting diodes are in the current path. The center-tapped rectifier gives a peak output of Vp minus Vd, while the bridge rectifier gives Vp minus 2 Vd. However, the bridge rectifier has a lower PIV requirement. Its PIV is Vp minus Vd, which is only about half of the center-tapped value, 2 Vp minus Vd. That concludes the introduction to rectifier circuits. Please look forward to the next lecture. See you next time. Bye-bye.